Okay, guys, here we go. Can you guys see me and hear me and see my slides? Also, I'm curious how many of you, if anyone, is on the VCU network right now because there may be some outage issues. So if you're on the VCU network, can you type like on the VCU network in the chat box so that I can... Okay, so lots of people are not connected to the VCU network. Okay, perfect. Thanks. That's good enough, guys. Thank you. Okay, so let me get myself organized here a minute. Okay, so today we are going to keep on our track and keep moving through chapter 8. I do have a couple of quick announcements for you guys. As you guys know, there's an Achieve homework assignment and the quiz on chapter 8 will both be on Monday. I'm also going to set Monday as the deadline for getting full credit on the extra credit chart. I'll be talking about that for the next couple of slides, so more on that in a minute. But Monday will be when you need to upload your completed chart to Canvas for the full amount of extra credit possible. Of course, you can always turn things in late for part of the full amount of the extra credit possible. The other major announcement that I need to make is that my normal office hours today have to be shifted back because I had a conflict. So my office hours today will be shifted back. They'll be between 4:30 and 5:30 p.m. today. And then also I'm adding in some office hours tomorrow morning first thing. And I'll be trying to add in more office hours over the course of the next couple of weeks as we finish out the semester, in part because we're learning a lot more reactions, and so it's just a lot more to digest, and I want you guys to have as many chances as you can to make sure you have the material down. And also in part because, as you guys I'm sure have seen the announcements, the SI sessions for this class are not going to be taking place anymore this semester. And that is just due to extenuating circumstances and things outside of anyone's control. So I will do my best to pick up the slack there. And what I'm hoping to do is to kind of get into a cadence beginning next week where I can try to have both some open office hours that are like we have been doing, where you can stop by and ask me any question you have. And also some more SI-like office hours where I'll let you know in advance and we'll be working through some problems together. So without any further ado, I'm going to go ahead and move along into the details of chapter 8. And this is just a reminder of where we've been. We've already covered almost just about half of this chapter. And really, this is the meatier half. This is the more important and the bulkier half and the more kind of fundamental half, if you will. And today we're going to finish that up and then go through some of the next couple of topics here, which are each kind of very individualized and still very useful and very functional reactions, but they're not kind of the workhorse reactions that these ones that we've already covered are. So I mentioned that I was going to take a couple of minutes to talk about this chart. I introduced this chart to you guys at the very tail end of lecture on Monday, but I wanted to take a couple of moments in a sort of a more controlled fashion and talk to you a little bit more about the details of this chart. This chart can be really helpful for you guys in terms of organizing your thoughts about chapter 8 and organizing a lot of material, because chapter 8 is very dense. And so what I've done is I've shown you that there's a chart in your book. This is actually table 8-1 in your book. And this table has sort of condensed all of the reactions that you're going to be learning or that you have learned in chapter 8. And a couple of things, I showed you guys this slide briefly on Monday, but I want to take a moment and really highlight some key points that I didn't have time to at the end of class on Monday. This chart is a very, very condensed version of the material that you're learning in chapter 8. So if we look, for example, at HX addition, which is how we started this chapter off, it tells you the type of reaction you're doing, HX addition. It gives you the other name for it, hydrohalogenation. And then note that below the arrow in brackets, it says HX. And that HX is telling you that HX is overall what gets added across that double bond. And in a big red box, because it's so important, I boxed it. I want to make sure everyone realizes that these are not necessarily the reagents that you use to achieve this transformation. So this HX in these brackets is only representative of the atoms that are added across that double bond and not necessarily the reagents. And so for the case of HX addition, you actually know two different sets of reagents to do this HX addition. And if I back up a little, you'll be able to see it. You know, an electrophilic HX addition, which you can do using HCl or HBr or HI that goes in a Markovnikov orientation. And you know how to add HBr in their radical mechanism when you add it with peroxides, which because of that different mechanism undergoes anti-Markovnikov orientation. So just again, to kind of drive that point home, this one entry on the chart is actually representative of two separate reactions that you know, and just kind of be aware of that it is a condensed version on this chart. Like I mentioned on Monday, I do think that this chart is an excellent way for you guys to study and to really kind of get your mind organized around the different reagents and the different stereochemical outcomes for each, not just each category, but each reaction within each category that we've talked about. And of course, I do think this chart is good for you to study, but I also think it'll be good for you guys to take the time to kind of reorganize your own notes. And that's why I provided you that blank chart scaffold, which I'll talk about over the next couple of slides. So I want everyone to take this chart from your book and build your own version of it that has more information, that is a little bit more expanded and not so condensed as the chart in the book. And as I mentioned, you'll be able to submit your filled in chart for extra credit. And I'm going to have this due on Monday so that you can use it as a study guide for your chapter 8 quiz. Now, keep in mind, you cannot use your chart when you take your chapter 8 quiz. I'm having you make this chart to help you organize your thoughts, but then when you take your chapter 8 quiz, you have to put that chart away. It's going to be a closed book, closed notes quiz, and you cannot use your chart no matter how tempting it is. And that also brings me back to another point, that this chart, the one that's in your book, after you've made your own expanded chart, this chart will also be a good chart for you to kind of go through and quiz yourself in almost like a flashcard fashion to help make sure that you've got, you're remembering all of the details of each of these reactions. Okay, so regarding the chart, what I've done with the chart has been to take each category of the chart and I expanded it for you. So for example, let's keep talking about HX addition. We have taken HX addition and we've learned two different reactions that can affect this. One does Markovnikov and the other does anti-Markovnikov. And this is the same entry from the chart, but you can fill out two different rows of this chart because they have different reagents, they have different intermediates or transition states, they have different stereochemical consequences. And so there's different columns of this chart that you can kind of keep track of all these very important things. And these are the things that you could get tested on, right? You could get tested on, hey, provide the reagents to do this transformation, or what is the stereochemistry of the product when I do a hydration using the oxymercuration, demercuration sequence, right? So all of these types of things are the things that you're going to need to know about. And of course, there's 2 pages for the chart because chapter 8 is really full of really useful and fun reactions. And we are right now we've gone through 2.5 rows of this chart. We'll finish up this bottom row today and we'll get through several of these rows on page 2. And you kind of have a hint here at the bottom just to kind of give you guys a heads up about what's coming. This chart covers chapter 8 and the reactions of alkenes. You're going to be able to apply a lot of these same things to chapter 9, which is the reactions of alkynes, just as a heads up about what's coming. If you think about alkynes, which are 2 pi bonds stuck in the same space, those alkynes can actually act very much like alkenes in terms of the types of chemistry they do. And of course, there will be some differences because they aren't actually alkenes, they're alkynes. But we'll see that a lot of the reactions in chapter 9 parallel the reactions in chapter 8. And so your studying for chapter 8 will do double duty, which is always nice. Okay. We're done with the chart. I'm going to move back into chemistry and the reactions of alkenes and picking up with halogen addition. So I talked to you guys a little bit about halogen addition on Monday. I'm actually going to start right over at the beginning of halogen addition because it was towards the end of class. So I just want to make sure everybody is with me on this. So let's do that. Of course, halogen addition falls into the same general category that we've been working with so far, where we can use these pi electrons in a nucleophilic way to attack an electrophile. And this is going to be when you can't figure out what else is going on. This should be your starting point for all of these reactions of chapter 8. If you have forgotten whatever those reagents are, look and try to find, is there an electrophile site in those reagents? And if there is, chances are your pi electrons are going to be involved in attacking that electrophile site as the first step in getting things started. So in halogenation, or addition of halogens across an alkene, we're going to be adding molecular halogens. So molecular chlorine, Cl2, molecular bromine, Br2. And what we end up with is two new carbon halogen sigma bonds that are arranged typically in an anti-fashion to each other. We'll see some examples coming up in the next couple of slides to make sure everybody understands what I mean by this. And what we get as the outcome here is these two new halogen bonds on the carbons next to each other. This is called a vicinal dihalide. The word vicinal just means neighboring or next to. You guys don't need to know that, but your book uses this term, so I didn't want to leave it out. I showed you guys this slide on Monday also, but basically bromine, molecular bromine or molecular chlorine, is electrophilic on one side because that sigma bond holding the two bromines together is a fairly weak bond. It can be broken such that those electrons go with the bromine that's leaving to make a great leaving group. And when that happens, of course, you'll make a new bond with your nucleophile. So you can see this happening with hydroxide, with ammonia. When it happens with a pi bond, however, there's a little bit of a difference here. When it happens with a pi bond, when you form this first sigma bond with the bromine, the electrophilic bromine, you still have bromide with the two electrons leave as a leaving group. But when you form that first sigma bond, at the same time, you're bringing these lone pairs of that bromine in proximity to what would have been a carbocation because you're using these pi electrons to create this sigma bond. And so that carbocation never fully forms because the lone pairs of the bromine are right there to help create a new bond and a more stable scenario. So what you get instead of a carbon-bromine bond and a carbocation is this three-membered ring that's called a bromonium ion. And this three-membered ring is, a highly energetic intermediate. It is electrophilic. And of course, we've also just generated a really great nucleophile. And that nucleophile can add back in to one of the carbons that used to be part of the double bond in an SN2 fashion and break one side of this three-membered ring. And we'll see it on the next couple of slides. So don't worry if that went too fast for you. We'll see it on the next couple of slides. So the first step in whether this is molecular bromine or molecular chlorine or molecular iodine, the very first step is making this three-membered ring, which the generic form is called a halonium ion. If this is molecular bromine, it's bromonium. If it's chlorine, it's chloronium. But overall, what we're doing is using the pi electrons to form one sigma bond of our three-membered ring, and the lone pair electrons of the electrophilic halogen atom to make the other sigma bond of our three-membered ring. And then, of course, we are breaking the sigma bond of our molecular halogen, and the two electrons from that sigma bond are going with the other halogen atom, okay? So two of these electrons came from the pi bond, two of these electrons came from the lone pair on this electrophilic halogen. And then our last set of electrons moving around, the sigma bond electrons became another lone pair on that halide. Okay, so what happens once you have this halonium ion is that, like I said, we've generated a good nucleophile when we had that bromine leave with the sigma electrons. This X minus, a Br minus or Cl minus, depending on what your original halogen was, this is a good nucleophile and it can attack at the back side of this carbon atom in an SN2 fashion. And so this three-membered ring is, of course, creating an electrophilic situation at these carbon atoms. This X is a good leaving group because if it leaves with these electrons from that sigma bond, it'll look like a normal halogen again, right? Full octet, no formal charges. And so our nucleophilic halogen can attack at the backside of one of the carbons that used to be part of the double bond. And of course, that facilitates bond breakage of one of the bonds of the three-membered ring. Okay, now you can see why the X is added or considered to be added in anti-fashion. I'll go into this more in the next slide. But this is essentially an SN2 reaction. It's a direct displacement using a nucleophile to displace a leaving group in a concerted fashion. So what do you think happens to the stereochemistry at this carbon if this is an SN2 reaction? It gets inverted. Just like in SN2, we invert that stereochemistry. And so let me talk about this in a little bit more detail over the next couple of slides. Okay, so with the addition of halogen to alkenes, there are really two different concepts of stereochemistry that are very important to remember. The first is called anti-stereochemistry. And this anti-stereochemistry is essentially the idea that our nucleophile is going to come in and attack our bromonium, or whatever our halonium is, from the opposite side of where that halonium has set up on that double bond, right? So our halonium in this case is shown as forming on the bottom face of the double bond. It's a three-membered ring on that bottom face. And so our nucleophile has to come in from that back side because it's an SN2 style fashion. And so that means that our new carbon bromine bond, the nucleophilic one, will be pointed up from the ring. And our original carbon bromine bond that was part of our bromonium three-membered ring will be on the opposite side of the ring, facing down in this case, but whichever way, if it's up or down, it's going to be opposite or anti-stereochemistry to the nucleophile coming in. The other thing that we need to remember is that because this is a backside attack and a concerted displacement reaction, the chirality or the configuration at this carbon center where this displacement is occurring, it will be inverted. And so this is considered a stereospecific reaction, meaning that exactly one stereochemical configuration is produced from this intermediate. Okay, so this is exactly identical to an SN2 reaction because it is an SN2 reaction. It's not just like an SN2 reaction with the same features. This step, which is the second mechanistic step of this addition of halogens to an alkene, this second mechanistic step is an SN2 reaction. And so it is subject to all of the same requirements and restrictions and consequences that an SN2 reaction is subject to. So another thing to point out is that, of course, we started out with achiral starting materials, right? These are not optically active, and we have not added any optically active reagents to our pot here. So even though we have, in this course of this reaction, we have created two new chiral centers, we will create exactly this anti-product and exactly the enantiomer of this anti-product. And the reason for that is twofold. It gets a little tricky here, but first, in this first step, that bromonium ion can occur by forming on the bottom face of the pi bond or on the top face of the pi bond. So that's one method to envision the two enantiomers forming. And the other is in this symmetrical alkene, our nucleophile can attack at the right carbon or it can attack at the left carbon. So that's another step where 50% of the time it would attack in one place and 50% of the time it would attack in the other place, because they are chemically identical to each other. They're equivalent to each other, and you cannot differentiate between those two. So statistically, that makes 4 different pathways, right? Top face or bottom face choice, and then left or right carbon attack choice. All 4 pathways happen, but they all result in anti-stereochemistry, either anti this way or anti this way. And so what you get is the 2 enantiomers of this molecule. Okay, so let's take a deeper, closer look at that when we can actually track our stereochemistry a little bit more carefully. So let's do a bromination on cis-butene. And if we add molecular bromine across this pi bond, you can have the pi electrons attack the bromine and the bromine lone pair come back and make the other bond of the 3-membered ring, of course, in a concerted fashion. And so if we make the bromonium on the bottom face of this pi bond, remember, because these the 6 atoms related to the pi bond right now are perpendicular to your screen. So if we have the bromine come in from the bottom face, and then to create the bromonium ion on the bottom face, and then our bromine nucleophile comes in from the top, it has to come in from the top and attacks the right side carbon, then what we get is this product that I'm showing you here on the right. If, on the other hand, that bromine nucleophile came and attacked the left-hand carbon while the bromonium is on the bottom face, we would get exactly the enantiomer, with the bromine sticking up this way and a bromine sticking down that way. So we would get the 2 enantiomers, shown here, both enantiomers as Fischer projections. Now, what happens if the bromonium ion comes to the top face? Because we know that can happen too. So if the bromonium ion comes to the top face and makes a bromonium on the top face, then our new nucleophilic Br- can attack from the bottom face. It has to attack from the bottom face because it has to attack from the opposite side of the bromonium. And if it attacks at the left-hand sided carbon, you get release of your bromonium to be over here, and you get this enantiomer that I've shown here. If it attacks at the right-hand carbon, you get the opposite enantiomer. So hopefully you guys can see that. And of course, statistics are how we determine the ratio. And so statistically, we're gonna end up with a 50-50 mixture and a racemic composite of our products. Okay, so here's something really cool. That was what happens when we have the cis-butene. What if we have trans-butene? Well, when we have trans-butene, the same 4 mechanistic pathways are possible, right? Bromonium can happen on the bottom or the top face, and then our nucleophile in each of those cases can either add to the right carbon or to the left carbon, but it has to add from the opposite face of wherever the bromonium is. So if our bromonium is formed on the bottom face of this alkene, and then our nucleophile bromide comes in from the top face on the right carbon, we get this compound. If you look closely at this compound, we could follow the other pathways, but if you look closely at this compound, if we rotate around this carbon-carbon bond such that this bromine comes down and is in the plane of the page, then this hydrogen rotates up and is facing back. This methyl group rotates up and is facing forward, and that makes this a meso compound with an internal mirror plane right here down through the center. So if you can't see that right away, don't worry about it. The other thing that you could have done and paid attention to is that if you do your bromonium on the bottom and then your bromine nucleophile attacks on this side, and so you get actually the opposite, what looks like the opposite configuration, you could have then had those 2 molecules and you would have been able to see that you could pick one up and overlay it with the other. Also, keep in mind that if you were to draw this one and essentially the same compound, but the meso compound, and not recognize that they were meso and say, well, I made these 2 enantiomers, that's still, if that's not full credit, that is almost full credit, right? Like we like partial credit here. So if you were able to kind of draw through this whole pathway, and you do the same thing down here and create the 2 Fischer projections or the 2 versions of this, and didn't recognize that they were the same as each other, that's like, 90-95% of the points still, because the meat of what we're doing here is making sure that you guys know the halogen addition and how the halogen addition works and the stereochemical consequences of it, which are that they have to be anti to each other, and that inversion occurs at one of the centers where that bromine nucleophile acts. Okay, so I am going to strongly encourage you guys to, on your own time, try to draw out these pathways. Take these two examples and draw out the mechanisms. Show yourself, convince yourself what happens when the bromonium ion forms on the top face, what happens when it forms on the bottom face, and what are the 4 different pathways that can get you to these enantiomers. Try it out on your own. There's nothing like practice to help this kind of settle in. Okay, the final thing I want to say about halogen addition to alkenes, direct halogen addition to alkenes, is a really cool application that we as chemists have figured out over the years. So this is kind of an old school method as a chemical test when you have an unknown compound, how to begin to find clues to identify what that compound is. Of course, now in 2022, we have all sorts of instruments and equipment and mass spectrometry and all sorts of cool things, just like you see on CSI, where you can give your sample to an instrument and that instrument can figure a lot of stuff out for you. But back in the day when there weren't so many neat pieces of equipment, and really the other thing is if you're cost limited, all that equipment is really expensive. So back in the day, there used to be just a series of different chemical tests you could do on different compounds to find out what functional groups are present. So these are essentially like building individual clues in a whole big logic puzzle to try to figure out what is your compound. And this one is very relevant to this chapter. So this is called the decolorizing bromine test, and it tests for the presence of a double bond. And here's how it works. Bromine, molecular bromine itself, has this deep red color, a very, very intense red color that looks almost brown when it's concentrated. And so what happens is bromine has this color, but as you can imagine, carbon-bromine sigma bonds don't have this color. So if you have a double bond present, and if you add bromine, molecular bromine, to that molecule, this molecular bromine will get used up, and it will become instead 2 carbon-bromine bonds. And when that happens, you erase the color. So that's what's happening here on this left-hand side. You have molecular bromine, which is this deep dark red, and if you drop it into a solution that has a molecule that contains an alkene, that red color will disappear as the bromine gets consumed and used up and added to that double bond. If you have a solution of a compound that does not have an alkene in it, then you drop in your bromine and your bromine just sits there and you have this color still. So this is a really cool application of exactly what we've been doing, taking advantage of sort of visual cues and visual observations that we can make as chemists. All right, so that covers it for halogen addition. Hopefully this halogen addition reminded you of similar mechanistic ideas that we've already been talking about with addition to alkenes. I'm going to take this halogen addition that we just did, and I'm going to take it just one little step further to a halohydrin formation. This halohydrin formation is going to be exactly what it sounds like, so let me go ahead and show you. What we can do is modify a halogen addition using the specific way that we do the reaction conditions, to instead of generating 2 new carbon halogen bonds, generate a carbon halogen bond next to a carbon hydroxyl bond. So this halohydrin formation is called halohydrin, halo for the new carbon halogen bond, and hydrin for a new carbon hydroxyl bond. And basically, the way we're going to do this is do the halogen addition that we were just doing, but doing it using water as a solvent. And when we do that using water as a solvent, then water becomes the nucleophile instead of the X- that we released when we made our halonium ion. This should make sense because if water is the solvent, then we have a lot of water around. We have a ton of water around. and there's just more water molecules to outcompete the X minus as a nucleophile. So when we do this reaction, the halide is going to end up on the less substituted carbon. And so that makes this a Markovnikov orientation reaction. And I'll show you some examples of this on the next couple of slides to drive this point home. But the halide, remember, because we're going to be forming a halonium ion, that halogen is the electrophile. And so just like Markovnikov has described, our electrophile will end up on the less substituted carbon. So let's see what this looks like. The first step is identical to halogen addition to alkenes. The first step, you make your same halonium ion. You also still release your X minus. So we're breaking this XX bond and those sigma electrons are going with that X that's the leaving group. So same first step. This version has all of the arrows drawn in formally, whereas on the previous slides, I hadn't shown you all of the arrows for sort of simplicity's sake. But here you can really see the pi electrons forming one of these bonds and the lone pair electrons forming the other bond. Concerted reaction at the same time that those sigma bonds are leaving with the leaving group. All right, once you have that halonium ion, just like in the case of halogen addition, we do an SN2 attack, which requires a backside attack. It requires an anti-stereochemistry of the product. It results in an inversion of this carbon center. Everything here is absolutely identical as halogen addition to alkenes. The only difference is that instead of using X minus, we're using water as the nucleophile. And we're using water as the nucleophile because we have set our reaction up to use water as the solvent. So it is present in way more concentration than this X minus, and it literally just outcompetes based on sheer numbers. It outcompetes the X minus. All right, so in this backside attack, our lone pair from our oxygen does indeed attack this electrophilic carbon, breaking one of the carbon halogen bonds of our halonium. And then we just need to do this one extra step. As usual, we can't lose track of our protons and formal charges. So we do get a protonated intermediate that we then need to deprotonate, but we can do that easily using another molecule of water. And that's what gives us our halohydrin product. It does have anti-stereochemistry, just like with halogen addition to the double bond. And now we can give it also a Markovnikov designation, where we could not give our halogen addition a Markovnikov designation because both atoms are the same, right? How would you distinguish between the two atoms of the halogen? But now we can distinguish between the X and the OH. And we know that the X was our electrophile, right? We added to our electrophile right here. So our X is our electrophile bond. That X electrophile will end up on the less substituted carbon, making this a Markovnikov orientation. And I'll show you guys on the next couple of slides some more details on that to drive that point home as well. Okay, so here is the slide that really kind of shows in a visual way the Markovnikov consequences of this halohydrin formation. So here I've drawn out a chloronium intermediate, and just like the mercurinium ion, the two carbon halogen bonds of this chloronium are not identical. The one between the more substituted carbon and the chlorine is a weaker bond, and that is because there's delta positive spread across this whole triangle, right? And this carbon that has more substitution has a better capability to stabilize more of a delta positive. So that's where more of the delta positive will be, weakening this carbon chlorine bond relative to the other carbon chlorine bond, right? And so that is why when the nucleophile attacks, it is going to attack the carbon that is more substituted because that has a larger delta positive. This is not new. This is not new for you guys. What's new is that I'm applying it with a halogen, but we've seen it before already with mercury in the oxymercuration demercuration sequence. The more substituted carbon is the one that will be more delta positive and therefore more electrophilic and more susceptible to attack by the nucleophile. Okay. This sort of a concept is also true when we're doing halogen addition across the double bond. It's just that we can't tell which side the halogen ended up on because both halogens are the same, right? So here is our product, at least before deprotonation, our product of halohydrogen formation. And note that these are formed in anti-fashion to each other, right? But keep in mind also, we are going to form the enantiomer of this. So in this case, I'm showing the chloronium being made on the top face of the double bond. It is also at the same time, 50% of the time, being made at the bottom face of the double bond. But in both cases, the water is going to attack the more substituted side. So in both cases, you will get a hydroxyl group added to the side that also has the methyl and the hydrogen atom, and then a chlorine attached to the other side, but you will get both enantiomers at this position. Okay, and then of course, this is just a reminder that this is Markovnikov in its orientation because your electrophile, which was the chlorine, ends up on the less substituted carbon. All right, so just another couple of examples to help you guys kind of drive this home and see it in action. Here's cyclopentene. Cyclopentene pi bond can form a bromonium on either the top face or the bottom face. If it forms on the top face, that bromonium ion on the top face, you'll have water come in from the bottom face to attack at one of these two carbons and release that bromine so it's only attached to the other carbon. The stereochemistry of addition is anti, right? Because your hydroxyl group is going to end up in anti-position to your bromine. In this case, it doesn't matter which side the water molecule attacks because they were equivalent when this is a bromonium ion, as long as it's from the opposite face of where that bromonium ion is. So of course, we're going to generate not only this compound, but the enantiomer. Again, we cannot create optical activity. We can create these two chiral centers, but we're going to create them in a 50-50 mixture, but they will always be relative to each other in this configuration. The bromine will always be anti to the new hydroxyl group that has come in. Okay, so that covers us for addition to alkenes that fall into this kind of regular, kind of normal, if you will, electrophilic addition where we have those pi electrons attacking a normal electrophile. The rest of the chapter is going to be kind of specialized cases that don't always fit in perfectly to these types of categories, but many times still do. But each case kind of has its own quirks and its own specific deals to it. So let's go ahead and move on to hydrogenation of alkenes. So in a hydrogenation of alkenes, this is a catalytic reaction. And what we're doing in this hydrogenation of alkenes is that we're taking molecular hydrogen and an alkene, and in the presence of a catalyst, which is going to be a transition metal here, typically platinum, palladium, or nickel, when we have this catalyst can take molecular hydrogen and help it to add across this alkene. This reaction would not work without the catalyst. What we're doing overall is using the pi electrons of our alkene and the sigma electrons that we're holding our two hydrogen atoms together and using them to form two new sigma bonds, two new carbon-hydrogen bonds. So I'm showing you this example down below of how this works or how it might look in practice. If you have some kind of an alkene and molecular hydrogen, so H2, and you subject it to conditions of a metal catalyst like platinum, you end up adding these two atoms of hydrogen across this double bond to get butane in this case. So just a note, just a reminder, we've now taken a molecule that has 1 degree of unsaturation, 1 degree of unsaturation, and we have added hydrogen across it to get a fully saturated molecule with no pi bonds, no rings. All right, so this is actually a convenient way to create saturated alkyl chains, and yes, saturated fats. Yes, indeed, saturated fats. Okay, so the mechanistic sort of individual details of the mechanism are beyond the scope of this course. So that should be some relief for you guys. You don't have to know the exact details of all of the electrons moving around for this reaction, but there are some stereochemical consequences of the mechanism that you do need to know. So I'm going to go over those in the next 2 slides. When we do this hydrogenation of alkenes, again, catalyzed by a metal, typically that metal is a solid. There's typically like either a powder or something like that, where it's not actually in solution, it's actually a surface. And so what happens in this hydrogenation reaction is that the hydrogen, the molecular hydrogen, and that double bond sit down on the surface of that catalyst. They actually get adsorbed to the surface of that catalyst. Once that happens, the hydrogens react with the alkene, but they form their bonds across the same face of the double bond because the double bond is sitting down on that metal catalyst with using its kind of double bond, using its pi bond. So that results in both atoms of the molecular hydrogen. So both hydrogen atoms will be added to the same side of the double bond because of this mechanistic constraint. And so that's called syn stereochemistry. Just like with halogen formation, we learned that the halogen atoms add in an anti-configuration with anti-stereochemistry. This is the opposite of that, where we're now forming them with syn stereochemistry, where both hydrogen atoms are going to end up on the same side of the double bond. So what does that look like? Well, here if we have an alkene that we've labeled with deuterium so that we can track things more easily. If we take this alkene and subject it to hydrogenation over platinum catalyst, then we'll see that both atoms of our hydrogen add to the same side of the double bond. In the example I'm showing you, they're adding to the bottom face of the double bond. 50% of the time, they'll add to the top face of the double bond. It turns out in this case, this is a meso compound, right? It has an internal plane of symmetry right here. And so you would have normally gotten the 2 enantiomers in equivalent amounts, but in this case, the 2 enantiomers are the same compound. So you get just 1 compound out of this. But the key point here is that both of the hydrogen atoms end up on the same side as each other in syn stereochemistry. And I have another picture to show you guys this because I think visuals really help. Cartoons sometimes help. And so here's a cartoon for you. If you have your platinum catalyst, which again is a surface, and you have your alkene, in this case a cyclohexene, again labeled with deuterium, that alkene is going to sit down on that platinum surface. The molecular hydrogen has also interacted with the surface so that now the hydrogen atoms are actually attached to the surface. Again, you don't need to know the mechanism here. This is not really a mechanism, and I'm not telling you anything about what's going on with the electrons of the platinum, for example. But because this alkene has sat down with just the green side of its pi bond sitting on the platinum, both of these hydrogen atoms are going to add to the green side of where that pi bond used to be. So they're both adding to the bottom face of this alkene. And of course, here's our product with our 2 hydrogen atoms syn to each other on the same face of this ring. Even if this weren't a ring, those 2 hydrogen atoms would still end up syn to each other. It's just you might not be able to see it as easily because after they add, you could rotate this bond. But while they are adding, you cannot rotate this bond. So the syn stereochemistry is set by this hydrogenation. Okay. And then the other thing I want to say about this is we sat this alkene down on its green side, but it could have flipped over and it could have sat down on its blue side. And indeed, that would happen 50% of the time because we cannot create optical activity here. And in the case of this molecule, because the symmetry of the molecule, the internal symmetry of the molecule, both of the products would have been the same, but just be aware it's not specifically sitting down only on the green side, it's also sitting down on the blue side 50% of the time. All right, there's a question in the chat box that says, would syn stereochemistry usually be less sterically favored compared to anti-stereochemistry in any reaction? So that's a difficult question to answer because it really does depend on the mechanism and the type of question, the type of reaction in question. You can imagine that syn stereochemistry in this case would be typically less favored because the hydrogen atoms are small, and so therefore the other groups are probably big, and so you'd want to spread out your big groups. But what if your hydrogen atoms were the same size as your other groups? So it really depends on the situation. I think the better way to think about things rather than sterics is make sure you understand the mechanism of what's going on. And in the case of hydrogenation, the syn addition is dictated by the mechanism of this pi bond sitting down on the platinum catalyst on the surface of the surface of the catalyst. And likewise, when we do halogen addition or halohydrid formation, we're forming a 3-membered ring that is subject to an SN2 attack by a nucleophile from the opposite side. So in those cases, it's the mechanism that dictates it's an anti-stereochemistry, right? So it really depends. I'm very hesitant to kind of assign that kind of generality to the sterics here. And the question really should be about mechanisms. If you were to have some mechanism where you generated, for example, a carbocation intermediate, something that has an intermediate that has free rotation, then by all means, the sterics of whatever that rotational kind of space is would impact the product distribution. But in each of these examples that we've been talking about with hydrogenation and with halogen addition, we're not in a case where we have free carbocation intermediates. We have a concerted addition of an electrophile that kind of dictates the stereochemistry. And so you can use your chart to fill all this stuff out, right? And you can see why that chart is going to become kind of a critical tool for this chapter. All right, in my last couple of minutes left, I just want to introduce you guys to cyclopropionation. I think I can do it in the 2 minutes that are left because it only has a couple of slides, and we'll save epoxidation for Friday. So cyclopropionation is exactly what it sounds like. So I want to take a minute to look at this word here. We are going to be making a cyclopropane out of an alkene. So we're going to take our double bond, and instead we're going to turn it into a 3-membered ring, right? A propane is a 3-membered ring. And because it's a cyclopropane, we know it's going to be a ring. And we're going to do this using a carbene, which you guys have met in chapter 4. So as a reminder from chapter 4, this is what a carbene looks like. It is one of the types of reactive carbon intermediates. And I told you when I introduced this to you in chapter 4 that it would be not very prevalent throughout organic chemistry. That's a very rare type of reactive intermediate, but that we would see it once. And this is that once. So in our carbene, as you might remember, we only have 6 electrons for that carbon. So it is not a full octet. That's what makes it a reactive intermediate. It also has no formal charges, but it's not a full octet, so that's why it's reactive. Has a lone pair in a hybridized sp2 orbital. Those can be nucleophilic. Also has an empty p orbital, and that can be electrophilic. So what we're going to do is see that with alkenes, if an alkene and a carbene come to be near each other, they react in a way that gives you a cyclopropane ring. So the pi bond of the alkene acts like a nucleophile and adds its electrons into that empty p orbital on the carbene. And then at the same time, that lone pair from the carbene can react and form a new sigma bond with what would have become a carbocation if there weren't this reactive lone pair sitting right here next to it, right? So these two things happen in a concerted fashion. We're going to be forming both sigma bonds at the same time, both of these new sigma bonds at the same time. And there are 3 ways that we can use to create carbenes. So as far as mechanistically, this set of how you form the cyclopropane is the mechanism that I want you guys to be thinking about and remembering. But we can't just order a carbene up from our favorite chemical manufacturer because they're unstable, right? So what we also need to know in order to do a cyclopropionation is how can we create a carbene from a different reagent? And there are going to be 3 different ways of creating carbenes: diazomethane, a Simmons-Smith reagent, and alpha elimination of a haloform. So I'm out of time to tell you about these 3 things today, but I will post the slides for these 3 things. I will also go ahead and post the slides for epoxidation just so you guys can kind of see what's coming. And we will pick up here on Friday. And I can stick around for just a couple of minutes if you guys have any questions. And yes, I promise I will release the details for exam 2. You guys should already see the grades for exam 2. You should be able to see the grades for exam 2 already. Can you not see the grades for exam 2 already? I'll make sure all of that stuff is released before the end of the day today. I'm sorry about the grades. I thought you guys could see the grades already and just not the answers, but I'll make sure all that stuff is released today. All right, thank you guys. Make sure you work on your chart and kind of help with all of this kind of settling in and getting into your brains.
Dr. Belecki.
Okay. Some of you guys can see your exam 2 grades. I was pretty sure I released some, so I'll send an announcement once I make sure that you guys can see the content of exam 2. And then if you guys are still trying to figure out how to see stuff after that, please email me and I'll take care of it. Okay, did somebody have a question, or were you just going to tell me about the exam 2 grade?
I was just going to tell you about the exam 2 grade.
Okay, great.
Thank you.
All right, you're welcome. Thank you. Hope you guys all have a good couple of days, and I will see you on Friday.